Hello. In this video, I'm going to be showing you how to draw all the possible ketones and aldehydes from the given molecular formula. The first thing is to draw out all the carbons in the formula. We have a total of 4 carbons, so we start by writing them out like this. We're going to start with ketones. For this to be a ketone, the C double bond O must be between 2 carbons, which means that we can only add the double bond O on this carbon or on this other carbon. Okay, now I'm going to choose the second carbon. Once we've added the ketone functional group, next is to fill out all the hydrogens, making up the 4 bonds on carbon. But we also have to make sure we stick to the number of hydrogens that was given to us. So starting with this first carbon, I need 3 hydrogens to make up the 4 bonds. Okay. Now this carbon is full. This carbon is also full. It has 4 bonds. Now move on to this one. This will need 2 hydrogens. This will need 3 hydrogens to make up the bond. But based on what we have here, I only have 3 more hydrogens to go, which means that the number of hydrogens required here is more than what we need or what is in the formula. So we're going to have to add a double bond. Now we cannot add a double bond here because that carbon is full. We also cannot add it here because this carbon is full. So that only leaves us with one spot, which is between these 2 carbons. Now, after adding the double bond, fill out your hydrogens, completing the bonds on each of the carbons. So this carbon now is full with just 1 hydrogen. This one will require 2 more hydrogens in order to make it up. So now, once you're done, the next step is to confirm that the number of atoms in what you drew out corresponds to the molecular formula that was given to us. So here I have 4 carbons, 1, 2, 3, 4, and then you have 1, 2, 3, 4, 5, 6 hydrogens and 1 oxygen, and that's perfect. So that would be one of the first possible ketones from the formula. The next thing you look at is it possible to move around the atoms in this formula? Now, looking at this formula, if we move this double bond to the first side over here, that is not possible because that carbon is full. If you move it here, it's also not possible. So it can only be on that side. Now, if we decide to move the double bond O to the third carbon, that also doesn't work because that moves this to the first side. So you're going to end up having something that looks like this. Okay, all the strokes are hydrogens. Okay, I'm not writing them out. Now, if you have this, it is exactly the same thing as what you have on top. It's just a flipped version, more like you turned it the other way around. In naming, they're going to have exactly the same name because you're going to give priority to the ketone. The sides that give this ketone a lower number, that's where you number from. So therefore, they will end up having the same name. So this would not count as a second ketone. So the only way we can have a second ketone is to turn this to a cyclic form. Since we have 4 carbons, that would mean you have 4-sided cyclic structure, which is usually like a square. Now, each of these sides are your carbons, okay? So that's a total of 4. Now, because the sides are equal, you can add your double bond to any of the sides. I'm going to choose this side. You can add it on any side, and it's going to be the same. So that will be another ketone. Confirm that your atoms are the same with the formula. So this carbon has 2 bonds, which means there is 2 hydrogens here. Same as here. Same as here. That makes it a total of 6 hydrogens and 1 oxygen. So 4 carbons, 6 hydrogens, 1 oxygen, and that's what we want, right? So that means that this can be another ketone. The next one is turning this to a three-sided cyclic form instead. Now, since we have 3 carbons, it means that we need to have an extra carbon on one of the sides. So let's start with the ketone. If I add my double bond O here and add the carbon on this side or on this side. Now, it doesn't matter if you add it here or if you add it here. The reason is when naming, this is going to have your priority. So if you are starting 1 here, this becomes 2. If you add it to this side, this also now becomes 2. So whether you are putting it on the right or on the left, it doesn't matter. Okay, so now we have a total of 4 carbons with the addition of the methyl group. And now let's count our hydrogens. This carbon right here is full, so there's no hydrogen. This has 2 bonds, so it's going to have 2 hydrogens. This has 3 bonds, has 1 hydrogen only. And then this carbon right here has 3 hydrogens because you only have 1 bond. So there's going to be 3 hydrogens there. So with that, we have 6 hydrogens in total, 4 carbons, and 1 oxygen. At this point, there's no other ketone possible from that formula. These are the only 3 that can be possible because no matter how you rearrange this, you're going to get exactly what you already have. So let's look at the aldehydes. I'm going to start with writing out all the 4 carbons again. Now, aldehydes are terminal functional groups, which means that they are always at the end or at the beginning. They cannot be in between carbons. So if I'm starting from the beginning here, this is my aldehyde functional group. So after writing out the functional group, the next thing is to fill out your hydrogens. This first carbon would need 2 hydrogens to be full. And that leaves us with 3 more hydrogens to play with. But since this carbon will need 2, this will need 3 hydrogens. It means that the hydrogens remaining is not enough to fill out all the carbons, which means there has to be a double bond again. Okay? So with this double bond, this carbon will then only need 1 hydrogen. This will need 2 more hydrogens to fill up the bonds. And that makes it a total of 6 hydrogens. And that's what is in the formula. We have 4 carbons, 6 hydrogens, and 1 oxygen. So that is a possible aldehyde from this formula. The next one is moving the C double bond to another position. So let's try that. If we maintain the aldehyde functional group exactly where it was before, writing out all our carbons, but then instead of the double bond being between the 3rd and the 4th carbon, we put it between the 2nd and the 3rd carbon. So with this, this will only have 1 hydrogen. This will also have only 1 hydrogen, while this would have 3 hydrogens. Confirm that the number of atoms are correct. I have 1, 2, 3, 4 carbons, 1, 2, 3, 4, 5, 6 hydrogens, and 1 oxygen. So that's perfect. So that's another possible aldehyde from this formula. If you name them, their names are going to be different. Okay. And because they are different, they are different aldehydes. They are not the same. So now we can try a cyclic form. But in order for us to have an aldehyde, it has to be 3-sided, because 4-sided would be a ketone, because you will have a carbon that is in a terminal position. Okay, so if we do 3-sided and then add the extra carbon on any side, like we always say, since the 3 sides are equal, it can be on any side. I prefer here. Now this carbon will then bear the double bond O and H. That's the aldehyde functional group. Now let's confirm if this is okay. So if I have 2 hydrogens here, because that already has 2 bonds, another 2 hydrogens here, and then over here, this is 3 bonds, so it only has 1 hydrogen. So I have 1, 2, 3 carbons plus this other carbon, that's 4. and then 1, 2, 3, 4, 5, 6 hydrogens and 1 oxygen. So that is perfect. So these are all the possible ketones and aldehydes that we can have from the given molecular formula C4H6O.